I request all the participants to fill up the feedback form for the session 1 for today's FDP program. Soon we'll be closing the link. Now we welcome. So good afternoon, sir.
Yes, Sami.
So dear participants, welcome to the second session. Now, sir will enlighten us on the second topic of today's session.
Sir, shall we start, sir?
Yes.
Okay, sir. Now you are the presenter, sir. Thank you. Sir.
Okay, friends. Are you able to listen to me? Hello?
Yes, sir. Your voice is clear.
Clear. What about the screen?
Screen is visible, but your PPT is not open, sir. Once again, just close and open once again. అవునవును సార్ది ఇనిషియల్ ఓపెన్ అవుతుంది. ఉన్నారు సార్ కానీ లేదా మళ్ళీ ఒకసారి అవుతారు అనుకోండి. వచ్చారా? ఓకే, నేను ఇక్కడ ప్రజెంట్
Sir, now you can share your screen. Sir,
Think this.
Sir, sir, so when we press screen, sir, we have two options, sir. We can share screen. We can share screen or application, sir. Applications, the PPT which is opened, you just share that one, sir.
Applications.
Yes, sir. When we press when we press screen, sir,
Ah,
we'll get both screen and applications. In applications, your PPT, whatever is open, it will, you can see that, sir.
ఏంటి ఓపెన్ కావట్లేదు.
Full screen mode. Full screen mode. Yeah.
Okay, is visible clearly?
Yeah, sir. It's clear. It's clear now.
Okay, okay. Welcome, friends, to this second session. So in this session, I will be talking on the developments and challenges in casting process, in the sand casting process. Okay. So in the previous session, we have seen developments and challenges in the investment casting process. Now I am talking about the sand casting process. Now, this is the classification of the casting process. One is the conventional molding process, broadly if we classify. Second one is the chemical sand molding process. Third one is the permanent molding process. And fourth one is the special casting process. So under the conventional molding process, we have green sand molding, dry sand molding, and flashless molding. Under the chemical sand molding, we have shell molding, sodium silicate molding, no-bake molding. Under the permanent molding process means where the molds are made up of metallic dies. One is the gravity die casting and the other one is the pressure die casting. And coming to this special casting process, one is investment casting process, continuous casting process, vacuum sealed casting process, squeeze casting process, centrifugal casting, plaster molding, evaporative pattern casting, ceramic shell molding, slush casting, and steel casting. So let us, these topics are too many. In fact, maybe a complete semester is required to learn all these. We are not going to learn all these in this session. Just for a overview, I have shown you these topics. Now, let us concentrate about the conventional molding process, means the sand molding process. So in this, we have the green sand molding, dry sand molding, and flashless molding. Let us see how these have been developed. Next, let us go to the challenges in the sand casting process. Now, first one is the green sand molding process. First of all, what do you mean by green? Green means the presence of moisture. When the moisture is present in the sand, we call it as the green sand molding. So this is how a green sand mold looks like. So generally we use two molding boxes. One is the drag, another one is the core. And this is the cavity, a cylindrical cavity you can see here. And this is the core. A core, so molten metal is poured through this pouring cup. This is the sprue and it falls into the sprue well. And this is the runner and it passes through the runner and it flows around the core like this and it rises. And here it solidifies, and after solidification we have to break the sand, we have to separate the cope and the drag, and we even have to destroy this cope. Then we have to take the casting outside. Here green sanding molding looks like this. So this is the lower box drag and this is the upper box cope. Yes, molten metal is poured into the mold. Now, advantages of the green sand molding: most of the metals can be cast by this method. Most of the metals and most of the alloys can be cast except titanium alloys. And pattern costs and material costs are relatively low. And no limitation with respect to size of the casting. A small casting, maybe of the order, maybe 0.5 kgs or even 200 grams can be made by sand casting. And even a casting up to the weight of 5 tons, even 10 tons can be manufactured, can be cast using sand casting. So these are the demerits of the green casting. Poor surface finish. In that there is no doubt. Poor geometrical accuracy, machining is required to achieve the finish on the product, and improper proportions of the moisture result in casting defects. Next one is the dry sand molding. So this dry sand molding is the green sand molding only, but it is modified in the sense that before pouring, the moisture is totally dried out. The mold is baked in an oven at about 200 to 310 degrees centigrade. So the reason is the moisture in the mold may react with the molten metal and form gases and porosity defect, gas defects inside the casting. So to prevent this, so we use the dry sand molding. Advantages of the dry sand molding: defects that arise due to the moisture will be eliminated in this case. What are the demerits? Drying of the mold requires oven and they consume power, electricity. Next one is the flaskless molding. What do you mean by flaskless molding? Means in the other two cases we have used the flask, the coke box, the coke, and these are drag. So these are the molding flasks. We are using molding flask, but here in the molding flaskless molding, we don't use any molding box or any flask, molding flask. You see here, so this is the molding sand, comes like through this. And here, so this is the pattern. What is the distance? Hello? Okay. You see here, this is the pattern. This is the pattern of molding sand. Mold and they are assembled here. You see, in a similar way, they are produced and they are assembled. You see, and molten metal is poured. When the molten metal is poured, do you think any flask is supporting the mold? No flask. So that's why this is known as the flaskless molding. Advantage of the flaskless molding: the rate of production is high and fettling requires lesser efforts. Why? When the molding box is there or when the molding flask is there, destroying or breaking the mold is difficult. Here it is very easy. And what are the demerit? The demerit is the system requires mechanization. So that increases the initial cost, initial establishment cost. So now let us come to the challenges in the sand casting process or the casting defects. So let us see the casting defects in the sand casting process. So what is a defect? First of all, a defect is an irregularity in the casting process that is undesired. Any irregularity that is undesired. So some defects can be tolerated while other defects can be repaired. Otherwise, they must be eliminated. Means what does it mean? Some defects can be managed. Okay, even if the defect is present, still you can work with that. That is the tolerated. Some other defects can be repaired. For example, so there is a crack on a casting. On a big casting, there is a small crack. So that can be welded. So that is the repairing. Sometimes the crack is too big or there is a severe porosity defect, shrinkage porosity defect. That be the case, what to do? There is nothing that we can do except that it should be rejected. It should be melted inside the furnace again. Now, let us see the classification of defects. So the defects in the sand castings can be broadly classified into 6 types. One is the defect due to the elimination of gases. Next one, defect due to pouring of the melt. Pouring of the melt means something is wrong in the molten metal. Next, defect due to metallurgical factors. Next, defects caused by the means in the molding sand, something is wrong. Next, defect caused due to other factors. Defect due to shifting. So these are the broadly 6 classifications in the and first we'll see the technical of cases. Now, blowhole, red tape, dispersion case, and blister. Now, what are these? This is the typical appearance of see, it looks like this. You see, on you see prominent pores. So that be the case, the casting has to be rejected. There is no point in accepting this, and it leads to loss to the industry. Now, what are the causes? Excessive moisture in the mold, slag in the molten metal reacts with the carbon and liberates carbon monoxide, and iron oxide on the mold reacts with the carbon in the metal and liberates Siva. So this Siva is responsible for the blowhole. Not only Siva, the excessive moisture. So when the excessive moisture is present in the moisture sand, the molding sand, this moisture comes in contact with the molten metal and turns into vapor. Similarly, the slag in the molten metal, what is this slag? The slag in the molten metal contains silicon dioxide that reacts with the carbon and forms carbon monoxide. Same is the case with the iron oxide. Iron oxide means iron FeO. So from there, the oxygen is coming and reacting with the carbon in the molten metal and forms carbon monoxide. Now, what are the remedial measures? Provide vent holes. Excessive moisture should be avoided. Avoid excessive moisture, and excessive compaction should be avoided. Once you compact too much, what will happen? The mold becomes too hard and the permeability comes down, and the moisture, the gases cannot escape. Extra care to be taken to segregate the slag from the liquid matter and avoid using rusted chills and chocolates. We use chills and chocolates in the casting process. Why? Chills are used to enable directional solidification, and chocolates are used for supporting the pores. Sometimes these are rusted. Rusted means that is iron oxide. So once there is iron oxide, so there is oxygen component. That oxygen component reacts with the molten metal and forms carbon monoxide. Next, let us see the pinhole porosity defect. Now, this is the typical appearance of pinhole porosity. You can see large number of uniformly dispersed tiny holes. Means the size of this hole will be as small as the head of a pin, small pin. So that is the meaning of the pinhole porosity. Too many such holes are there. Why? The reason is hydrogen is the responsible for element for the pinhole porosity defect. So the molten metal, especially if you consider aluminum alloys, they readily absorb hydrogen. So this hydrogen, while melting, it is absorbed by the molten metal and it comes along with the molten metal, and while the hydrogen is still present inside the molten metal, we pour. And during solidification, this hydrogen slowly comes out and it forms a pinhole porosity on the surface of the casting. Now, if you see this graph reveals one interesting fact. What is that? At solid state, the aluminum or the metal has a minimum absorbability, you see. But in the liquid state, and its solubility, hydrogen solubility is almost 4 times than its solubility in the solid state. Remedial measures: vacuum melting means the melt means the charge or the unmelted alloy is to be melted in a vacuum. Next one, if you are not able to use a vacuum furnace is very costly. So you can use the ordinary melting and go for the vacuum degassing. Next one, avoid very high pouring temperatures. So we always used to give superheating. Suppose, for example, the melting point of aluminum is 660 degrees centigrade. So beyond 660 degrees is the melting temperature. So beyond that, we heat by another superheat, maybe another 75 degrees, maybe we heat up to 725 degrees, or in the worst case up to 750 degrees centigrade. What happens if someone melts it, heats it up to 850? It overboils. Then it accumulates air bubbles inside that, and that could lead to pinhole porosity. So the superheat should be optimum. The superheat should not be too much. Next one, let us see the rat tail effect. So if it looks like this, it's an irregular depression on the surface of the casting, similar to a rat tail impression. What are the causes? Moisture in the molding sand, evaporated turns into steam, and steam forms a thin layer on the moisture between the surface and metal casting, metal being solidified. So finally it leads to the defect like a rat tail. So what are the remedial measures? Measures should be taken to reduce this defect. Additives like wood flour can be added to the sand to reduce the mold sand expansion. So this arises due to the molding sand expansion. Next one, let us see the dispersed shrinkage. Yes, it looks like this. Small shrinkage dispersed cavities throughout the casting. What are the causes? Excessive moisture and very high pouring temperature. What are the remedial measures? Appropriate moisture and pouring temperature to be taken. Next one, the blister. You see, this is the typical appearance of a blister. Means this is a casting, no doubt. Now, here you can see something like a bubble like pump. You can see here, so something here. So this is the blister. What are the causes? Gases trapped in the cavity cause depressions on the mold surface. Means there are gases in the cavity. They are able to cause depression on the mold surface. Why? Because the strength of the mold is very poor. Means the compaction is not sufficient. So the insufficient strength of the mold cavity at some locations. Remedial measures ensure sufficient and uniform compaction of the mold. So we have completed the first category, defect due to the evolution of gases. Next, let us see the defects due to the pouring of the melt. Under this category, we have misrun, we have cold shut, we have elephant skin, and we have inclusions. So let us all see all these one by one. First, let us see the misrun. Misrun. Now you see, this is a casting, and it's a casting having some 5 ribs, you see. Now you see this rib, this is perfectly cast, and this rib is perfectly cast, this rib is perfectly cast, even this one. Now coming to this rib, there is some discontinuity, don't you see? So this is that misrun. This defect is known as the misrun. Now the question is, why does it arise? What happened exactly? Can you imagine? The molten metal was not able to flow properly in this region. So that is the reason for this misrun. Now again you see here. So here there is a discontinuity. Molten metal could not flow properly. So this is the misrun. Now again you see. So this is there is a discontinuity here. So this is the misrun defect. Now this is a turbine blade, and the blade is supposed to have this profile, you see, like this, but there is a discontinuity. Again, same in the case here. This blade should be like this. There is a discontinuity. Why? The cross section or the thickness of this fluid is not so much, very small. So the molten metal could not flow through that thin section. That is what exactly happened. Now these are the causes. Insufficient fluidity, first one. Low pouring temperature, too small ingots, and low pouring temperature. Now what are the remedial measures? Increase pouring temperature. Once you increase the pouring temperature, so remember in the casting we come across two temperatures. One is the melting temperature and the other one is the pouring temperature. Melting temperature is something which is just enough to melt it. Maybe if you melt aluminum up to 660 degrees centigrade, it starts melting. But that is not enough to pour. If you at 660, if you start tapping, the moment you tap, it solidifies. So it should be at a higher temperature so that you can take it, carry it to the mold and pour. So that higher temperature is the pouring temperature. Maybe 725 degrees or 750 degrees. So as you increase the pouring temperature, what happens to the fluidity? The fluidity will be increasing. The viscosity will be decreasing. So fluidity will be increasing. So the pouring temperature should be increased. Next one, increase the pouring speed. That also will help us to minimize this defect. Make ingots larger. So with this we can minimize the or prevent the misrun defect. Next one, cold shut. Now what is cold shut? What is cold shut? Now you can see a casting here. So this is a casting. Now here is one ingot. Means of course you can imagine a runner in front of this casting. And above the runner there was a sprue. And through that sprue molten metal is poured. And through the runner molten metal is supplied to this ingot. And molten metal is supplied to this ingot. And these two streams are coming together inside the molding cavity. Right? And they will come together and these are to be mixed perfectly without any discontinuity. But it so happened that there is a small hidden and invisible separation, discontinuity is there. So when we break this mold and we take a single casting, apparently we don't see any discontinuity, we don't see any separation, but internally there is a separation. So when we use this component in the practical application, yes, it will fail. So that is the cold shut. Now, why it is happening? Longer distance between the ingots. That is the main reason. Next one, large surface area to volume ratio. Now, suppose the distance is too much, then what will happen? Initially, the molten metal had sufficient temperature. The temperature was high. So because of that, the fluidity was high. But as it was coming closer to inside and inside, it comes in contact with the molding surface. Then what will happen? Its temperature slowly comes down and comes down. By the time it comes to the center point, what happened? The temperature has almost come down, almost come to the melting temperature. And the other stream comes, the melting temperature of these two streams is too small that they are not able to mix with each other. That is how this discontinuity is arising. So the longer distance between the ingots should be avoided. Try to maintain minimum distance between the ingots. Next reason is the geometry of the casting is such that it has large surface area. It is possible that for the same mass of the casting or for the same weight of the casting, one casting can have large surface area, another casting can have small casting surface area. Then what will happen in the case of the first case, is the casting having large surface area, then that is in contact with the molding surface, molding sand. So because large surface area is in contact with the molding sand, within short time, what will happen? It will be dissipating heat rapidly. It will dissipate heat to the sand mold, and the molten metal inside the cavity, it loses its temperature abruptly. Then what will happen? Maybe two streams are coming, and no doubt the distance may not be too much. The distance is fair and acceptable because the casting's surface area is too much, it has already dissipated the heat to the surroundings, and by the time the two streams are coming to the center, they have lost their heat energy, and the fluidity has abruptly it has come down, and these two streams are not able to mix with each other. So that is finally there is a discontinuity between these two streams. So large surface contact area also is another reason for the cold shut. Now, how to prevent this cold shut? Use more number of ingots. Instead of using 2 ingots, you can use 4 ingots. Next one, increase the pouring temperature. So with these remedial measures, we can prevent the cold shut defect. Next one, elephant skin. What is this elephant skin? If it looks like this, extreme case of magnesium silicate contaminated in the melt, you see it looks like this. It's a rare defect and rarely used defect, rarely spoken defect, rarely feared defect. Melt is contaminated by the magnesium silicate and it is deposited on the casting surface like this. Ensure proper separation of the slags. So that's a slag. So that should be removed from the melt. Next one, inclusions. Now, what is this inclusion? Undesirable foreign material present in the metal, those foreign materials could be oxides, slags, or dirt. So they come along with the molten metal, they enter into the cavity, and after the casting is solidified, they are deposited on the surface of the casting like this. So these will be peeled off, and ultimately we see a depression on the casting or a discontinuity on the casting. So that is the final result of this inclusion. So this inclusion must be removed from the casting. And here you can see this is the inclusion defect. What are the main sources of inclusion? Slag, metal, oxidation products, refractory materials, refining agent residues, molding materials, and erosion products of the mold. So they all come along with the mold and they are deposited somewhere on the surface of the casting. So these are known as the inclusion. Certainly these cannot be accepted on the surface of the casting or inside the casting. Now these are the sources: eroded paints, indigenous inclusions, non-dissolved inoculants, and many more. How these are harmful? Deterioration of the casting surface quality. So this is one bad effect. Another one, deterioration of the mechanical properties. If these inclusions are going inside the casting, what will happen? The mechanical properties will be altered. Deterioration of the machinability. If it appears somewhere on the surface or somewhere on the machined portion, so machining would become a difficult task. Next, casting leakage and formation of the gas bubbles. Remedial measures. One is skimming of the molten metal before pouring. So there will be a centrifuge. So using the centrifuge, we have to do the skimming. And all these oxides and all the foreign materials, they have lesser density. Because of that, they are collected at the top and they can be removed as you keep skimming it. Choosing a molding sand with adequate strength and placing, the most important thing is placing exothermic foam filters inside the gating system. Once we place these foam filters inside the gating system, all these unwanted oxides or the foreign materials will be removed. Now, So this is the position of the filters, where we can place the filters. Vertical positioning, horizontal positioning, and vertical positioning in the filter. Next one, horizontal position of the filter, slanting position of the filter. You can see here, so this is the gating system, and this is a sprue, and this is the runner. And here, so this is the filter. The filter is kept here. Now you pour the molten metal like this from the top, and the molten metal passes through the filter. As it passes through the filter, all the unwanted oxides, unwanted foreign materials, all the ceramic materials will be filtered. Only the pure alloy metal, liquid metal will be passing through the filter, and it will be going inside the mold cavity. Next one, horizontal positioning. You can see there is another position. This way also the filter can be placed. Next one is the vertical positioning of the filter in the distribution. You see, somewhere here you can place the filter. Horizontal positioning of the filter, one more position, and like this. Next one, slanting position, like this. Now these are the foam filters. They look like this. So they are available in different sizes, different shapes. They are available in circular shape, and they are available in rectangular shape. They are rectangular shape. They are available in square shape, different shapes and different sizes. It all depends upon your requirement. What is your requirement? What is the size of your gating system? Accordingly, you can go to the market and you can purchase the foam filters as per your requirement, as per your convenience. And these foam filters are to be kept inside the gating system. Once you place these foam filters inside the gating system, so these inclusions problem can be avoided almost. Yes, these are the foam filters. You can see here, a foam filter is kept in a horizontal position. Now, until now, you see this is the sprue, and the sprue, the molten metal is poured. Until then, there is a, means I'm telling another advantage of this filter. Until now, the molten metal is traveling in a turbulent flow. You see, there is a turbulent flow, and once the molten metal passes through the filter, you will see a lamellar flow, which is good. So we have completed the first two categories. Now let us come to the third one, defects due to the metallurgical factors. Under that we have the hot tears. What is a hot tear? A hot tear is a crack arising during solidification. You can see this is the casting, and this is the pouring cup, this is the sprue, and this is the runner, and of course a core is kept inside. As we wanted a hollow cylindrical casting, and during solidification a crack occurred. So this crack is known as hot tear. There are four reasons for the hot tearing. First one is the differential contraction of the casting during solidification. Differential contraction means what? You see, inside there is a core. It could be a metallic core. After solidification, it will be removed. Now, during the solidification, this outer ring wants to contract. And because the core is inside, the core is resisting the contraction of the outside casting. So there is a conflict. So because of this conflict, there is a crack. So this is the differential contraction of the casting during solidification. Next one, the casting could not undergo shrinkage during solidification due to the casting design. You see, this is the casting. Now it has two ribs, two vertical ribs, and they are joined by a horizontal rib. Now the whole thing is inside the sand mold. Now it can so happen that the inside rib is more exposed, its surface area is more, so it solidifies quickly. It solidifies quickly. Then once it solidifies quickly, the contraction starts. It wants to contract. But what happens? The vertical ribs are fixed. They are not allowing the contraction of the central rib. See, again there is a conflict. So because of that, again there is a heart tear. Okay. Now let us see the third case, chemical composition. The chemical composition influences the heart tearing. See, for example, you take the cast iron. What is the composition of the cast iron? Cast iron is no doubt the base element is iron, but the main alloying element is iron. The iron, it contains carbon up to 2.1%, right? And it contains silicon 1 to 2%, and it contains manganese 1 to 2%. Then it contains phosphorus 0.6%, the typical composition, the typical proportion. It also contains sulfur 0.06%. Actually, that also can be avoided by the industrialists, but they allow it. Why? This sulfur improves the machinability. When we are machining, this sulfur enhances the machinability. So they allow this small amount of sulfur, that is 0.06% of sulfur. Now, it can so happen that without your intention, the sulfur content becomes more than 0.06%. Then what will happen? It influences heart tearing. Next one, the fourth reason is the long freezing range. It influences the heart tearing. Long freezing range, for example, say aluminum. What is its melting temperature or freezing temperature? 660 degrees centigrade. That is the melting temperature. What about tin? 232 degrees centigrade. So what about if you take an alloy of aluminum and 10% tin alloy, what about the freezing range? The freezing start for aluminum, freezing starts at 660 degrees centigrade, and for tin, the freezing starts at 232 degrees centigrade. Means the freezing range is nearly or more than 400 degrees centigrade. Now, it can so happen that what will happen? So the inside during solidification, grain formation takes place. Okay. Now, initially the aluminum grains will be forming, and once the grains are solidified, they undergo shrinkage, salt shrinkage. So during that shrinkage, the tin is still in the liquid state, right? So the tin goes where there is a shrinkage of aluminum and supplies the liquid metal. And again, this process continues. Aluminum still undergoes shrinkage, and this tin, which is still in the liquid state, goes and supplies liquid metal and fills that gap. So that is how it prevents the shrinkage defect or any discontinuity. It prevents the discontinuity. Now, what will happen? Let us consider aluminum. Now, in this case, we are considering aluminum 10% or aluminum 20 or aluminum 30%. So, in fact, these alloys are used in the bearings. Imagine a case. Don't consider aluminum 10%. Consider aluminum and say 2% tin. Until now, we are using aluminum 10% tin. So, what is happening? Aluminum grains are forming. So, as the grains are solidifying, this the tin, which is in the liquid state, is going and supplying where there is a discontinuity and preventing any kind of discontinuity or any kind of cracking or tearing. When you use this tin in the extremely small amount, maybe 2% or 3%, what will happen? Yes, in the initial stage of the solidification, yes, that there is a 2% of tin or 3% of tin. Yes, it is in the liquid state, and it goes wherever there is a shortage, wherever there is a contraction, it goes and supplies the liquid metal. But once this 2% or 3% tin is completely consumed, what will happen? Aluminum still undergoes contraction. It wants, yes, I need some metal. There is a gap. There is a discontinuity. Come and help me. There is no tin available. And if this situation persists, yes, there is more and more contraction. Finally, it leads to heart tearing. So this is the major factor responsible for heart tearing. So long freezing range can strongly influence the heart tearing in casting. So when we choose an alloy, so what is the freezing range? we have to see if we are using, there are 2 elements or 3 major elements. So what is the freezing range we have to calculate? So see that the freezing range should be minimum. If just imagine in this place of tin, you imagine magnesium. Aluminum's melting point is 660 degrees centigrade, or the freezing point is 660 degrees centigrade, right? Magnesium only 10 degrees less, 650 degrees centigrade. Suppose you use a casting, make a casting of composition aluminum 97% and magnesium 3%. Then what will happen? Yes, there is no doubt. There is initially the grains will be forming, aluminum grains and magnesium grains, but it won't be as in the case of the aluminum 3% tin. So there is a local contraction. Whereas when you use magnesium, where the freezing range is very, very small, the contraction will be there, but that is not local contraction. That will be a global contraction. So because of the global contraction, this hot clearing won't take place. So we have to ensure that the freezing range should be minimum. So these are the remedial measures for hot clearing. Use exothermic pads. Suppose you construct this point, so this the inner section has already solidified and it wants to undergo contraction, but the other portion is not alive. So what you can do is you can put a exothermic pad around the inner inner section. So because of this exothermic pad, so the heat dissipation will be slower. It takes longer time for solidification. Maybe it solidifies parallel along with the other 2 sections. So the whole casting is solidifying at a time, not different regions at different times. So this problem won't arise. Second reason is control the composition, minimize the sulfur content in the liquid metal. Doesn't mean that you should totally avoid it. Next one, use grain refiners. We have grain refiners available in the market like aluminum 8 boron, aluminum 3 boron, aluminum 3 titanium, aluminum 5 titanium 1 boron. So these are the grain refiners. So these can be added in the liquid metal while it is still in the furnace, extremely small amount, maybe 1% of the grain refiner. In the worst case, 2% of the grain refiner. When you add these grain refiners, the grains will be refined. The chrome coarse grains will be made finer grains. So these finer grains will help us to prevent the hot tearing. Next one, exploit the benefit of the residual and alloying elements. What is this? See, in fact, we have worked on this. So how to exploit the benefit of the residual and alloying elements. For example, we have conducted experiments with the aluminum and 1% tin. Just now I have told you, means the 10% proportion is extremely small. 1% tin. So when we have added 1% tin, yes, there were prominent cracks. You see here, these are the cracks. And what we have done is, later, we have added iron. It means initially we have made 6% aluminum 30 Fe master alloy, and out of that we have added 6% of this iron master alloy to this casting. Means to the 1% aluminum, 1% tin. Then what happened? This iron helped us to prevent the hot tearing. Then we started investigating how the addition of iron can help us to reduce the hot tearing or to prevent the hot tearing. Yes, when we have investigated in the SEM, we found this kind of leaf-like structure at several places. You can see these are the grains, you see, grains and a kind of leaf-like structure. So when we have analyzed it and under the SEM, we have seen that these are the iron-rich phases. Because we have added iron master alloy, so these are the iron-rich phases. Now, we have found out the chemical composition of these phases, means this leaf-like structure. You can see aluminum, tin is 10%, and iron is, you see, about 11%. Okay. Again, you can see here. So this is the leaf-like structure. Then what exactly happened? So this iron, what about the freezing point of iron? The melting point of iron is about to say 1100 degrees centigrade. So its freezing started below 1000 degrees centigrade or much higher than where aluminum starts freezing. Do you agree with that? So before aluminum started freezing, this iron rich phase has already solidified and it has become hard and strong. And when the aluminum grains were solidifying, and once solidification is over, when they were trying to undergo shrinkage or contraction, these rich leaf-like structure has held them together. Means they were anchoring them together. They were not allowing them to move. That is how the hot tearing was removed with the addition of iron. Now, what we can conclude with this? Iron can help us to prevent hot tearing in the aluminum castings. So most of the times when you buy raw aluminum or aluminum ingots from the market, don't think that it is pure aluminum. It always has certain miscellaneous elements. For example, if you buy the commercial aluminum, no doubt the major proportion is aluminum, but it contains say 0.5% to 1% silicon. It is good. It improves the fluidity. Silicon always improves fluidity. It also contains iron, 0.5% iron. So that iron really helps us to prevent the hot tearing. Sometimes there were cases where because the commercial aluminum contained some small amount of iron, the people have rejected it. Now we recommend that you need not reject it. If there is a small proportion of iron in the commercial iron, like say up to 0.5% or 1%, that will help us to prevent the hot tearing. Similarly, another investigation we have made. So we have added nickel to the aluminum 1% tin. When we have added nickel, again you see there was no hot tearing. It was like this. Again we have investigated why with the addition of nickel the hot tearing has completely gone. Why it was removed? When we have investigated under the SN, we see again a hard aluminum nickel rich phase was here. You see, hard aluminum nickel rich phase. Again we have analyzed under EDAX. You see, this is aluminum proportion 5% and nickel you see 16%. And this nickel freezes at about 800 degrees centigrade. You see, what about aluminum? It freezes at about 600 degrees centigrade. This nickel freezes at about 800 degrees centigrade. So before the aluminum started solidifying, the nickel grains have already solidified. They have become hard and strong. When the aluminum grains started undergoing solidification, and after the solidification was over, when they were about to become smaller or when they were about to undergo contraction, this nickel-rich phase was holding them together and prevented any further movement. That is how the hot tearing was prevented. Now, nickel is a common alloying element. So fortunately, this nickel helps us to prevent hot tearing in the aluminum castings. Next, let us see the molding defects caused by the molding materials. Under that, we have scab, metal penetration, flash, runout, lug. First, let us see the scab. So a scab looks like this. So this is the surface of the casting, and above the surface of the casting, you can see a thick deposition. What is this deposit? This deposit is a mixture of molten metal and molding sand. Means it has become a hard ceramic, hard lump deposited on the surface of the casting. Now, this is very difficult to remove. If you try to machine it, after all, it has become a ceramic, so it is very difficult to machine. So this problem or this defect is known as the scab. Now, what are the reasons or what are the causes? Low moisture content in the molding sand, below 3%. So the molding sand was loosely bound. Another reason could be low clay content, insufficient clay content. So we have to add moisture content, we have to add sufficient clay content, so that when we mix the molding sand should be sticking to each other particle very tightly. There should not be any loose contact. But it so happened that moisture content is less, the clay content is less, so the moisture part, the sand particles are not bound perfectly. They are loosely bound. So when you pour the molten metal flows through the gating system. As it is passing through the gating system, it pulls the sand particles because they are loosely bound to the mold cavity, and those sand particles are carried along with the molten metal, and they come to the molding cavity, and they are deposited and solidified on the surface of the casting. That is how the problem arises. How to prevent this? Regulate the moisture and clay content. Don't use too much moisture content. It doesn't mean that you should use too less content. The moisture content should be sufficient. And also the clay content should not be too much. If the clay content is too much, the mold becomes very hard and strong, and it becomes very difficult to break it after the solidification is over, and also the permeability becomes very poor. So the clay content should not be too small. If it is too small, this kind of defects will arise. Defects like the scab will arise. So the moisture content and the clay content should be moderate. They should be optimum. Next one, metal penetration. What is this metal penetration? Yes, again, it is similar to scab. You can see a deposit here. You can see there is a deposit here. Unwanted deposit. Metal deposit. It is not a deposit mixed with molten metal and molding sand, but it is only molten metal. Why it is happening? Of course, this can be cut and it can be removed. But why we should waste of time to cut and remove it? It is wastage of time, wastage of energy. Why it is happening? Large sand grains and insufficient compaction of the sand. Sand grains are so large that there is a significant gap between the neighboring sand particles, and molten metal is able to penetrate into the gap between the neighboring sand particles. Then what will happen? The molten metal penetrates into the molding sand, and the unwanted deposit is created on the surface of the casting. Same thing can happen due to insufficient compaction of the sand also. How to prevent this? Use fine sand grains. You should not use coarse sand grains. Use fine sand grains. It doesn't mean that the sand should be too fine. What will happen if it is too fine? The permeability will come down. Reduce casting temperature. Apply sufficient compaction of the mold, and use additives in the molding sand. Now, what will happen when we use the additives? Additives means, for example, coal dust is one additive. Let us see what will happen when we use the coal dust. So these are the molding sand particles. You see, these are the sand grains. So to these sand grains, the coal dust is applied. Mixed small amount of coal dust, maybe 3% of coal dust. So this coal dust makes a coating around the sand particles like this, like this, like this. Then these coal dust particles, they produce carbon monoxide, because coal dust contains carbon, right? And they react with oxygen in the atmosphere and they form carbon monoxide. Now the molten metal is coming. This is the molten metal. Now these are the sand grains. Without this carbon monoxide, the molten metal can come and they can penetrate between the two sand grains and form the penetration defect. But because we have mixed the coal dust, what happened? The coal dust produced carbon monoxide, and this carbon monoxide is pushing a pressure in the opposite direction. The molten metal is coming from right side to left side. and it is trying to penetrate into the sand particles, and carbon monoxide is exerting pressure from left side to right side. So that is how the molten metal cannot enter into the small gap between the sand grains. So when we add the coal dust, which is an additive to the molding sand, the penetration defect can be reduced. Next one is the flash. What is this defect? Yes, it looks like this. Actually, the casting is this one. This is the casting. This is the casting, and this is the region between the along the parting line. Means between the cope and the drag, there is a space. There is a line, parting line. So that surface on the cope box and the drag box, they should be perfectly leveled, so that when the cope is placed over the drag, there should not be any gap. But it so happened that there was some gap. So when you pour the molten metal has filled the cavity, but it has also flown along that unwanted gap between the cope and the drag. Now what to do? We have to put efforts. We using some machine. We have to cut this unwanted portion. So the time is wasted and the energy is wasted. So how to prevent that? First of all, the cause is the sand is not properly compacted along the parting line. Small gap exists between the cope and drag. So the molding sand should be leveled properly along the parting line. So that is the only measure we can take. Next one, runout. It's a defect similar to flash. Runout. What is this runout? You see here. So this is the casting, and somewhere the molten metal has run out from the molding box or from the along the parting line. It has a run out and it has made thick projections like this. You see? So these are known as the run out projections. Why it is happening? It happens due to the hydrostatic pressure. So when you pour the molten metal, as the molten metal is flowing through the gating system through the sprue, the molten metal exerts hydrostatic pressure, due to which there will be a tendency on the cope to raise up. So during pouring, the cope box may raise slightly for short time, maybe for few seconds. During that time, the molten metal will be running out and solidifies as a thick projection. So this is an unwanted case. So this has to be prevented. How to remove it? Place some weight over the cope before pouring the molten metal. So this is the molding box, you see. So this is the drag. So this is the cope. Some weight is kept. In fact, this is the practice in every casting industry. They place some weights on the cope so that during pouring, due to the hydrostatic pressure, the cope will not raise up and this runout problem will not arise. Next one, let us see the lug. What is this lug? Lug is metal solidified in the cavity surrounding this mold, you see. So this is the lug. So this is similar to the, we have seen earlier one defect called, what is that? Sometime back we have seen, do you remember? Penetration. So it is similar to that one, but there is a difference. Some portion of the cast contour are broken off in the mold area after withdrawal of the pattern. So it is not, in the previous case, the molten metal has penetrated between the larger sand grains. Then it has formed an unwanted deposit, but this is not that case. Here, somewhere inside the molding cavity, some portion is damaged or some portion is broken. Because of that damage or because of that breakage, there is a molten metal is going and solidifying in an unwanted portion. So that is how this unwanted projection is arising. This can happen if the handling of the molding box is not proper. Check for pressure points and broken up ridges. If something is broken, you repair it before the molten metal is poured. Next one, defect caused due to other factors. What are they? Mismatch and hot cracks. First, let us see the mismatch. Now it is like this. So this is a single casting. So what happened is this much portion is kept in the drag and this much portion is kept in the cope. Strictly speaking, so this much portion should move. Maybe it has moved by maybe 1 inch or 2 inches. So this line should coincide along with this line, but there is a shift. So this is known as the mismatch. Now this casting is useless. This should be rejected and it should be again melted in the furnace. Why it is happening? Again, you see, there is a casting and there is a shift. So this portion is cast in the drag and this portion is cast in the coke and there is a shift. Misalignment of the molding boxes. The coke and the mold should be perfectly aligned so that there is no deviation, no displacement from the expected positions. Now, what to do? Ensure proper alignment of the molding boxes. So for that, we use the dovetail pins. Both the coke box and the drag box, they have brackets in which there will be holes. In these two holes, a bolt will be kept. So this bolt will ensure that there is no shifting of the coke over the drag. So that is the usual practice. But what can happen is, as you keep using it for several years, maybe let us imagine there are two brackets for the coke and the drag, and there is a hole. Maybe the diameter of the hole is 10 millimeters. 10 millimeters hole on the bracket of the coke, same hole on the bracket of the drag. And through these two holes, a bolt of diameter 10 mm will be inserted. Now, as you keep using it for several years, the diameter of the bolt will be undergoing wear. So the diameter will become 8 millimeters or 7 millimeters. So when you pass a bolt of diameter 7 millimeters through a hole of 10 millimeters, what will happen? There is always a possibility of shift of the two boxes by a distance of 3 mm. That is enough. So that is how the mismatch problem occurs. So these worn out dovetail pins must be replaced periodically. That is very important. Next one, hot crack. What is this hot cracking? Sometime back we have seen. So that is hot tearing, right? So this is hot cracking. What is the difference? Hot tearing arises during solidification, whereas hot cracking arises after solidification. So that is the difference. Yes, generally this hot cracking arises for very large castings. Now you see, this is a big casting, so there is a crack, and this has arisen after solidification, not during solidification. What are the reasons? During cooling in the mold, during knockout. During knockout means what? After the solidification is over, we break the sand. During the breaking, so if the breaking is too rough, then it is possible that someone can hit the casting, solidified casting, and the solidified casting can undergo cracking. During cooling after knockout, yes, during cooling, so if there is a uneven cooling, that can result in the knockout. Or during heat treatment, after the casting is taken out, the heat treatment is given in some cases. And during this process, it can so happen that some portions may be having some large, some sections having larger surface, in which case they absorb more heat, they undergo more expansion. Maybe a neighboring section has a lesser surface area, it receives less, absorbs less heat, undergoes less expansion. So there is a difference between the expansion. That is how this cracking occurs. Okay. So it can also happen due to uneven cooling conditions and differential contractions. Remedial measures: use chills. Chills are the steel blocks which are kept inside the molding boxes, so that there will be uniform cooling of the casting. Next one, use fillets. These fillets also will help uniform cooling. Avoid rough handling. After the pouring is over, after solidification is over, and especially be careful during the knockout process, be careful during the heat treatment process, then this process can be minimized to a greater extent. And finally, we are coming to the last category, that is due to the defect due to the shrinkage. We have completed 5 categories. Now let us see the last one, defect due to the shrinkage. That is the shrinkage cavity. Shrinkage cavity. Solidification causes a reduction in the volume in almost all the metals. So every metal undergoes shrinkage except cast iron. In the except cast iron, what will happen? The carbon in the cast iron is in the form of the graphite. So graphitization takes place. Because of that, there will be bulging and the volume will be increasing during solidification. Now you can see here there are 3 types of shrinkages for any metal. One is the liquid metal. See, in a vessel or in a container, we have poured the molten metal. Initially, it is like this. Now we have seen there are always 2 temperatures for any cast metal. One is the melting temperature. The other one is the pouring temperature. Pouring temperature is always higher than the melting temperature. Maybe higher by at least 100 degrees centigrade above the melting temperature. Now, when you pour the molten metal at the pouring temperature, what happens? It slowly comes down, the temperature comes down. From the pouring temperature, it comes down to the melting temperature. For example, if we pour the molten aluminum at 750 degrees centigrade, then from 750 to 660, it will be in the liquid state only during that stage. Now, during that stage, there is a liquid contraction, liquid cooling. So, during this liquid cooling, there is a contraction. You see? So, this is the liquid contraction. Remember. So, this liquid contraction will be there whenever we are making a casting. Next one, you see, again, this is the reduction in height due to the solidification shrinkage. You see, now it has come down to the melting temperature. Once it comes to the melting temperature, there is no liquid change. There is no further change in the volume due to the temperature drop. In fact, during the transition of the phase, the temperature remains constant. Okay, but there is a shrinkage. This is known as the solidification shrinkage. So far, we have seen one is the liquid shrinkage, the other one is the solidification shrinkage. During this shrinkage, the temperature remains constant till the solidification is completed. After the solidification is completed, it becomes a solid one. Then there will be a solid cooling. Maybe from 660 degrees centigrade to it comes to room temperature 40 degrees. Then during this time, what is that? Is it liquid cooling? No. Is it liquid cooling? It is not liquid cooling. So it is solid cooling. So due to solid contraction, we use the contraction elements in the pattern. Okay. Now, if there is no razor, you see, this is a casting where there is no razor. Now you see there is a shrinkage cavity. So here is a shrinkage cavity. Okay. Now causes insufficient size of the razor. That is the first reason for the shrinkage cavity. Improper positioning of the razor, premature freezing of the liquid metal in the razor, abrupt changes in the casting design. So these four factors are the factors responsible for the shrinkage cavities in the castings. Remedial measures. Design the razor sufficiently larger. And second thing is ensure directional solidification. What is this directional solidification? Now you see here, so this is a casting. This is the casting and this is the razor. This is the razor. Now, the solidification starts from the end of the casting, means near the mold wall, the solidification starts. You see, and it is starting towards, means it is starting from right to left, like this. The solidification is propagating. This is known as the directional solidification. Now I will show you another solidification. That is the progressive solidification. Progressive solidification starts from top to bottom. You see, the solidification is also propagating from top to bottom. That is also there. Now, solidification is carried out in two modes. One is the directional solidification, another one is the progressive solidification. Now, if you want to, both in any casting, both the solidifications will be there. Both directional solidification and progressive solidification will be there. But which solidification is better for us if we want to prevent the shrinkage effect? Either the directional solidification or the progressive solidification. Just imagine there is no directional solidification, only progressive solidification is there, and this progressive solidification is starting from top to bottom, and it comes and this is solidifying, and it comes down, and it is, suppose it closes here. Imagine, and here there is a region which is not solidified. And razor is still having liquid metal, but it is not able to supply because somewhere the progressive solidification has dominated and it is not allowing the liquid metal to reach the area where there is a shrinkage. Now you tell me which solidification is good? Is it the progressive solidification or the directional solidification? Right? Certainly, directional solidification is better, but we can't make the progressive solidification zero. Progressive solidification will be always there. Only thing is, you see that the progressive solidification is smaller and the directional solidification is larger. Ways to achieve directional solidification. Locate razors away from the sections with ratios so freezing occurs. First in these regions, right? Next, use chills at required locations. Modify the casting design such that it ensures directional solidification. Next, use the blind razor. Next, use the exothermic material on the top of the razor. Next, cover razor with insulating compound or pad. Use chills at the required locations. You see here, in this case, there is gas porosity or shrinkage defect. The razor is here and this portion is solidifying first, and the other portion is the portion on the right side is not able to receive the material, liquid metal from the razor. Why? Because the central portion is already solidified. So we have to prevent this. So for this purpose, we can use the chills. Next one, say here again we are using chills. In the absence of the chills, there will be a shrinkage defect. Why? Because this portion is taking larger time for solidification, and when you use the chills here, so these chills are the metallic pieces, so they absorb the heat rapidly and they ensure that there is no shrinkage cavity at the center. Next one, modify the casting design such that it ensures directional solidification. Now you see, this design is poor. This design is poor. In this condition, and if you keep somewhere the razor somewhere here, it may not feed this portion. But in this case, in fact, you modify like this, and the razor will be somewhere here. Yes, it can supply the molten metal to this region. Modification of the casting design. You see, use ribs or fillets to improve the solidification. So this is a poor design. You see, in fact, it can be modified like this. If rib is kept here and a fillet is made here, so this will help us to improve the solidification. Modification of the casting design. You see, here we have made a taper. There was no taper here. So by making a taper, what we have done is we have initiated the solidification here, and the solidification propagates. So by making the taper, we are able to achieve the directional solidification. Next, use blind razor. Now, for the prime reason for the shrinkage defect is the prime reason insufficient molten metal in the razor. Now, do you know one fact? The efficiency of an open razor is only 15%. Means, suppose if there is a 1 liter liquid metal in an open razor, only 150 cc is used for feeding the casting. The remaining 850 cc is underutilized, because before it can feed the casting, it solidifies. The efficiency on open razor is only 15%, but we can't prevent open razor because it is not on. It is razor. It's a razor. It gives us an indication that the casting is fed with the molten metal. So, in addition to the open razor, we can also use the blind razor. So this is the blind razor, you see. So this is the pouring basin, sprue, and this is the blind razor, and this is the open razor. This is the open razor, and this is the blind razor. So the efficiency of the blind razor is 70%. Do you know that? So when you incorporate blind razor, the possibility of the shrinkage defect comes down. Next one, use exothermic material on the top of the razor. Now, these are the exothermic material. What will happen? You see, this iron oxide and aluminum. So, when this mixture is kept on the top of the razor, what we want, what is the problem with us? The efficiency of the open razor, just now we have seen that it is only 15%, 1.5. We want to improve or increase the efficiency of the open razor. Suppose if someone makes the efficiency of the open razor to 100%, it will be a wonder. But that is not possible. Maybe from 15% to 50% we can make. That itself is a big achievement. Or from 15% to 60% we can make. That itself is a big achievement. How we can? Why? Let me ask you this question. Why the efficiency of the open razor is only 15%? When we pour 1 liter of the molten metal, why only 150 cc is utilized for feeding the casting? Because other portion also wants to feed the casting, but before that other portion wants to feed the casting, it is solidified. So it is going into a helpless situation. Somehow, if we make that remaining portion also to remain in the liquid state till it feeds the entire casting, then the efficiency of the razor is increased. So that is what we are doing by using the exothermic material. So this exothermic material is a mixture of iron oxide and aluminum. So this mixture is kept on the top of the razor. Once you keep it on the top of the razor, it suddenly undergoes combustion. And there will be a reaction, exothermic reaction, and large amount of heat is generated. So because of this large amount of heat that is generated, the portion which is about to be solidified in the razor continues to be in the liquid state for some more time. Then that liquid metal will continue to feed the casting. So that is how the razor defect, shrinkage defect can be reduced in the casting. Next one, cover the razor with insulating compound or pad. Yes, another defect, why the razor is solidifying early? Because it is in contact with the molding sand. it is dissipating heat to the molding sand. That is how it is freezing along with the casting. If the casting takes 30 minutes for certification, resin is also taking 30 minutes. Suppose if the casting is taking 30 minutes for certification, and if the razor takes 1 hour for certification, then a miracle will happen. The entire metal present in the razor will be utilized for feeding the casting, and the efficiency of the razor will be extremely high. So that is what we are doing using this insulating material. So here this is an open razor. So what we are doing is we are keeping an insulating material around the razor. So this insulating material around the razor will ensure that the heat is not dissipated to the molding walls. So the molten metal, liquid metal in the razor continue to be in the liquid state for several minutes, even after the certification of the casting. So till the casting is completely certified, till the every section of the casting requires liquid metal, the liquid metal in the razor will supply liquid metal, supply to the liquid metal to the casting. Why it is happening? Because we are using the insulating cover around the razor. So by using insulating cover around the razor, we can increase the razor's efficiency and we can decrease the shrinkage defect. Friends, in this section we have seen the challenges, we have seen the developments of the sand casting process, we have seen, and the classification of defects we have seen. We have first category, we have seen the defects due to the evolution of the gases and different defects covered in that category. Second category we have seen defects due
Hello? Sir, there is a little technical issue.
Hello? Please.
Sir, there is a little technical issue here, sir. We are trying to connect you back, sir, again. Just 1 minute, sir.
ఎంతసేపు నుండి వచ్చింది, ఎంతసేపు నుండి ప్రాబ్లం? అయితే క్లోజ్ చేసేయమంటారా?
సార్ కనెక్ట్ అయ్యాను.
Yes, Samir. If someone has doubt, you can ask our authority to close.
Sir. Thank you, sir. Sir, that was wonderful session, sir. That was an amazing session, in-depth knowledge that how the defects have been categorized into different categories, and you have explained very well, sir. Thank you very much for this wonderful session, sir. And I request participants, any of the participants, would you like to have any discussion regarding any doubts? Please unmute yourself and you can ask Professor any doubts. Okay, if there are no doubts, we would like to close this session. Sir, thank you very much, sir. I once again Thank you, sir, from my bottom of heart for your valuable discussion, sir, from the
Okay,
session 1 and session 2, sir. Thank you very much, sir.